Hello, everyone. My name is Dr. Clement Chumesi. I'm a medical statistician for the Norfolk Department of Medicine at the University of Oxford. So this particular YouTube video you are watching is part of a master class that I did for the National Union of Ghanaian Students in China. But it is open for everyone to watch and learn at their own pace. So please, if you are watching any other part apart from part one, don't forget to watch the previous part. So if you are watching part two, please watch part one and part two before you watch part three. If you are watching part two, please don't forget to watch the first part or first session before you proceed. Okay, so thank you very much, and I hope you enjoy the video. And please don't forget to subscribe. Your subscription is much really appreciated, and it is one way of supporting us, and we really appreciate it. Thank you very much. Enjoy. Cheers.
With that.
No problem.
Okay. All right. Thank you.
Okay, so should I just wrap up within 10 minutes and then I can take questions afterwards?
Yes. Yes.
Okay.
Yeah.
Yeah, because there's no time, I'm just going to wrap up in 10 minutes and I'll direct students to specific links. Fine. And remember, there are so many online, like that's the interesting thing. Now, learning is supposed to be easier than it used to be. There are so many online information. Sorry, there are so many online information on how to do anything in, let's say, R online. So personally, I keep telling students from my first YouTube video, I'll tell you that once you are able to import data, not just in R, even when you want to do SPSS, when you want to do STATA, when you want to do SAS, Python, once you know how to import a data into a software, the rest is just making use of the internet. Because when it comes to the programming languages, packages are only installed when you need to use a certain function, a customized function created by someone else. Okay. And when you go to a block, so for instance, let's say you want to do multi-state Markov modeling, there is a whole link on this. I think the beauty is that this is the kind of the experiment I wanted us to do. I'll add the link to it so that you can follow through the codes. Okay. So that you can
Okay.
follow through the codes. Yeah. I couldn't get time to develop all the codes. So I'll just add this link when you get to the multi-state bit so that you do it. And then for the classical survival analysis, so I'll just add a link to it. I'm just trying to say that there are links to everything. So let's say you went online, you saw this blog, and you've seen these things, library. The moment you see library, it means whatever is inside that library is a package you need to install in order to be able to follow through everything they've specified down there. Okay. So that's one
Yeah.
thing you should note, right? And anytime you are installing, they should be in parentheses. Okay. But when you are loading with a library, you can choose to bring the quotations or not. But if you are installing, you should bring the quotations. Okay. If you don't bring the quotations, it will come as an error. But if you are loading, but when you install only once and you don't have to install ever again. So that is why after I installed, I bring this hashtag. Hashtag means that it should treat now everything after the hashtag like a comment. Okay, or it means it shouldn't run if I run that function. It shouldn't run as a yeah. So the hashtag is just a way of commenting out or adding specific comment or whatever. If you don't add so for instance, if I want to write my name Clement, if I run this, it tells me it's an error. But the moment I bring an hashtag and I do this, it's not an error anymore. Fine. And all the codes in the Jupyter notebook, remember you can just copy and paste into R. And as a matter of fact, I've demonstrated how you can download it just as if you've done it in RStudio. Okay, but it helps especially those who are doing their PhDs when you want to. As a matter of fact, you can clearly see you can use it for presentation. So it means that you don't necessarily, yeah. So here, the next phase of the program outline was, oh, okay, that's fine. So this one is multi-state. Yeah. So the next phase of the program outline was just to talk a bit about what is statistical programming or mathematical programming and what is IDEs and so on. Yeah. So remember that programming is very broad. Like it's very broad. Just like even through going through what you've just learned today, you've noticed that. Please, can you see my screen?
Yes, we can.
Yes,
Okay.
yes. Done.
Okay. Just going through today's session, you've noticed that even when it comes to data, we have different data structures. We have different areas of application and so on and so forth. This is to say, when it comes to programming, there are a group of people, especially computer scientists, who actually employs programming the same way statisticians or mathematicians also do. But one thing you should notice that those who are most programmers or those from other, there are people from computer science and other people not from computer science whose programming expertise is just to develop applications. So developing applications, programming to develop applications is different from statistical programming to analyze data. So it means that never confuse yourself. When, let's say, you wanted to learn Python, and then you hear that someone is very good in Python, the first thing you need to ask is, what is the area of application? Because someone can be good in Python for developing games or applications, but a person might not be good in Python for statistical analysis. And as I've already said, the knowledge of programming, especially when it comes to statistical analysis, it complements, you have to add your statistical knowledge. So it means that when you are using the software, it's not the software that is telling you what to do. You should know exactly what you want to do. You should know that, oh, okay, for this data, I need to use ANOVA for this hypothesis testing because I have a continuous outcome and I'm comparing between three or more groups. But before that, I need to test for normality. If the data is not normally distributed, then I'm going to use a Kruskal-Wallis test, which is a non-parametric version to compare medians, right? Fine. So in that case, it means I'm going into the software, doing what I need to do. The software will not automatically tell you what to do. So I think one of the mistakes was back in Ghana, people thought I was so good in programming. But little did I know that I was making use of only packages. So if you use someone's package to perform an analysis, remember that if there's a package for something, don't create your own. You only create your own if the existing package cannot be adapted or adopted for what you are trying to do, or there's no existing function or package for what you are trying to do. Otherwise, there's no need to create your own function. Fine. But you notice that those who are doing lots of elementary stuff, most of the time, they are existing packages. But if you look at, for instance, this particular paper, which is published in the Bulletin of Mathematical Biology, it is actually the top journal for the Society of Mathematical Biology. So it means for mathematical biology in the world, for their society, that's their journal. So it's quite a heavy journal. But with this particular journal, so you notice that everything you see in this particular publication, right from, so I'm developing a stochastic simulation model, right from the stochastic simulation model, the algorithms you see here, let me just come there, all these mathematics and everything, including the algorithms you are seeing here, there's no package for it. So I have to develop my own codes to achieve that. Okay. I have to develop my own codes to achieve everything you are seeing there. So in that case, that is one of the instances where if you don't know how to create your own functions, it becomes a problem. Okay, fine. So it's just to say that statistical programming, you cannot do statistical analysis in a programming software without knowing the right statistical methods to use. So don't just talk about, oh, I want to know. Okay, so you meet someone, the person says, oh, I have been programming in R. Then oh, can you do this data analysis for me, or can you tell me how to fit a certain model? Remember, the mere fact that someone has used R for something else doesn't mean that they can use the same R for another thing. I'm just trying to say that the knowledge or whatever you want to do in R is dependent on your knowledge about the method you want to use. If you don't have the knowledge, make use of online resources. ChatGPT, make use of online resources. How to do this? Okay, so for instance, if you want to fit a logistic model, just go to Google, type how to fit a logistic model, a logistic regression in R. So for instance, if I type how to fit a logistic regression in R. So the most important thing is know how to import data, and that's all. You see, there are so many blocks. This blog, how to perform logistic in R, how to perform this, different blocks, and they are free online. So I just have to click on one of them and check which one is much more useful for me, and so on. And by the time you realize, you've also, I mean, yeah, I'm not even happy with this one, but I mean, then I'll go to the next one. Okay, this one is trying to explain stuff, and this one is doing stuff. Okay, this has fitted the model. And if I want to look at interpretation, it's even going through other models. I mean, is doing other goodness of first statistics, variable importance. It has done that, and so on and so forth, and trying to make predictions and so on and so forth. Yeah. So in that case, it means just using this. Once I'm able to import, it always starts with the data. So it always starts with a certain data. So once you replace this data with your data, then it means you should be able to what, adopt every other thing it's used. And remember, most of the time we split the data into training and testing. And then we use the training to fit the model and we cross-validate the model based on the testing set. I think I've already done that on the YouTube channel. A typical example of that is on the YouTube channel where we are, yeah, this one. So building and validating a predictive model cross-validation and accuracy. It was a logistic, it was using statistics to aid in forensic research. You can just watch that and you enjoy. Please don't forget to subscribe. Usually, most of my subscribers are not even Ghanaians, and it's quite unfortunate. Yeah, and because sometimes Ghanaians we need help, but we don't want to support. For me, the only support I can get is your subscription. So please don't forget to subscribe so that and you don't miss future, how do you call it, future uploads. Fine. So that is what I wanted you to note about statistical programming. That understand the theory or just know the theory. You don't need to understand the mathematics. Just understand when to use this method. Just like I've done today. Just understand when to use a particular method. Once you know when to use it, then you now search for how to do that in the software, online or in ChatGPT. Okay, so that's all I wanted to know. Okay, so the next thing on the list is what is an integrated development environment? I've already talked about that on my channel, but basically integrated development environment is basically called, the ID is integrated development environment. It's just a platform that we use to run programming softwares. So SPSS, for instance, it is an IDE to run SPSS. STATA Studio is an IDE to run STATA. So for R, we have RStudio. It is an IDE to run R. Jupyter Notebook, it is an IDE to run more than 30 programming languages. So at the moment, I have only R and Jupyter kernel that I'm using here. And that means I can run R and I can actually open Python and be running it alongside. And the beauty about Jupyter Notebook as an IDE, as you can see, once you have your code, the output is just underneath it. And the graphs you produce, you don't have to save them separately. You don't have to save them separately. If you now get access to the, how do you call it? If you get access to the, if you download it as an HTML file, just as we've downloaded it in my downloads, if I open on it and I want to save a particular graph, let's say I want to save this, which graph? Let's say I want to save this graph. I just have to right click and click save as the normal way and go and save it as a particular folder. And it will keep the resolution. And the beauty about R is that you can set your resolution. So for instance, if you look at this one, I've set my resolution to be 300 dpi. So this is to say, especially if you are publishing, you notice that most journals says that your resolution, your figures resolution should be at least 300 dpi. Okay, 300 dpi. And that 300 dpi is basically what I've just done here. Someone will say, why don't I make it 500? Remember that too much of everything is bad. So someone will say, oh, if I want my graphics to be the best, why don't I set it to 500? The more you set the resolution, then it becomes too good. By too good means it also becomes bad. But 300 is like the best standard that you can ever use. So all my publications, I set it to 300. Okay, so that's basically one of the fine. So it means that Jupyter Notebook, I would say, is the best IDE you should use, whether you are doing Python programming, C++ programming, or whatever you are doing. And RStudio can be used for now. So all the codes you can copy and paste in RStudio. And like I just showed you that I can also download it as an executable script. And the executable script is similar to download it as an RStudio script. And that's what I have I did earlier. So like the whole course, I've downloaded it as an RStudio script. But you notice that in the script, I don't see this is where I see the codes, but I don't see any graphs. I don't see anything. So if I send you this, you might not know, first of all, whether there's an error in my code, or you might not even know whether what this output, this one, if I run, will give me. Okay, so that's the whole point. But if you should run it from scratch, of course, you'll see the graphics under this session. And just watching the first YouTube video, you know how to use RStudio, how to install it. You know how to use RStudio, and then and so on. Fine. Okay, so back to yeah. So here the next thing is I just wanted you to note that there are instances where previously you've been doing your analysis in SPSS, but because you've come for this session and you've noticed how useful R is, one of the advantages of R is that there are certain complex statistical analysis that SPSS, STATA, and probably SAS cannot do. eViews, Minitab, those who use eViews, Minitab, Gretel, even GraphPad, Prism, all these statistical softwares, okay, Tableau and the rest, all those statistical softwares, what I'm trying to say is that there are certain advanced statistical methods that they cannot do. It is recently that SPSS is now having certain capabilities to do machine learning, but that one is in the newest version. Okay, I have the newest version on my Mac. That's the only instance. Another question someone will ask is it good to run R on a Linux machine or a Windows machine? The only difference is that for Linux machine, there are instances where you are doing complex simulations, and the simulations will involve, let's say, 100,000 iterations, sometimes 1 million iterations, and so on. Where each iteration, let's say, each iteration is like a simulated data. Let's say if each simulated data is taking, let's say, 10 minutes, and you are doing 100 million, or you are doing 1 million, it means that it could take you sometimes about 7 days to get an output. Most of the time, when you run a code in R at this stage, within a second, you get your output. But I just want you to know that a time is coming. So, for instance, this particular paper I was telling you about, okay, this particular paper. For these simulations, you are seeing them there like that. The truth is that it takes so much time. But if you can minimize or cut the time, if it is 7 days, you can reduce this to 5 hours. And how do you do that? We call it doing paracomputing. So paracomputing, remember that anytime you run any code in R, it is running on only one processor. Even if your computer has 7 processors, it's running on, for instance, my MacBook has 12 processors. Anytime I run this, it runs on just one processor. But if I'm doing, let's say, 4 loops or looping, and each iteration takes a lot of time, and I'm doing 100,000, 10,000, 1 million iterations, then you should be able to parallelize your codes. By parallelizing your codes means that you are setting the code in such a way that if there are 1 million, let's say 1,000 is running on a particular core, another 1,000 is running on another core, another 1,000 is running on a different core, and the performance on one core should not affect this performance on the other core. Meaning that if you do paracomputing, and your codes are running in parallel, it means that the speed or the performance of on one particular core does not affect the other. But if you didn't parallelize your codes, what it means is that you have to wait for one of them to finish before you go to the next, about 100,000 times or 1 million times, depending on if those who do a lot of multi-color simulations or those who do stochastic modeling and it's quite mathematical heavy. You now do paracomputing so that your computer, your looping would run on multiple cores to speed up the computational time. Okay, so that's what I wanted you to note. But in doing the paracomputing, it is easy to do that on MacBook or Linux machines than on Windows. Windows use something you call on MacBook, the function we use to do the looping is called MCL apply. That is on MacBook or Linux machines. And that one, when you are doing it on Windows, that function can only work when you set the number of cores to 1. But there's a certain package called par-L apply. That is also for a certain function called par-L apply. That is also for paracomputing on Windows, but that one, it takes a lot of time. And to set it up is not straightforward. You have to define many things. But on Linux, it's straightforward. And another thing is that graphics on on Linux is much more beautiful than Windows. So always Windows graphics, MacBook or Linux machines are output, the graphics, the resolution are quite clear. But on Windows, sometimes it looks a bit blurry. Although it's okay, it looks a bit blurry. So sometimes maybe the best thing is to export the data as a PDF. And there are ways to do that. You can just make use of ChatGPT, how to export a data from R as a PDF, and you should be able to do that. Fine. But that might preserve, PDF preserve data quality, or it preserves, how do you call it, the structure of the data. It's protected document format. So it protects it. So you can actually export it as a PDF, even if you are doing it in RStudio. RStudio, the graphics are sometimes terrible. You can export your graphs as PDF, and in the PDF format, you can always convert it to PNG or other format. Fine. So here we are just learning how to import different data structures. So imagine if you've been doing your analysis in STATA. Now you want to replicate the analysis you did in STATA in R. Or let's say you use STATA to do some time series analysis. You were doing some Granger causality test, something, and then you were told that you are supposed to do a nonlinear Granger causality test, and STATA cannot do that. And you want to do that in R. What I'm trying to say is that you can import that STATA data directly into R and use R to do that. Let's say your data was in SAS, and you want to change the SAS data to Excel, or you want to change the SAS data to STATA, or you want to change the SAS data to SPSS, or you want to change any data format to another data format. You can also do that. Now, let's see. So, for instance, this is there are packages you need to install. Okay, you install by using this, taking away the hashtag, but you only install a package once. Okay, once you install, and remember, you need an internet to install a package. Fine. But after installing a package, you don't need to install it ever again on your system. Fine. So here is a simple, but before then, there's something called setting a working directory. There are many ways to import the data into R, but the easiest of them all is set a working directory. Direct working directory is that I created a setting folder called Nooks China on my desktop. And I just went to copy the path. And copy it and paste it. But the take-home message is that those of you who use Windows, if you use Windows, this is how your path would always look like. It will look like a C and whatever, but it will be going this way. And then you see users, it will be going this way. Okay, like that. It will be two bars, and it will be going in the so it means this is like backslash. Okay, so those who use Windows, that's how yours will look like. It will look like that. Um, uh, like that. But those who use MacBook, it will be automatically in the /. You need it in the / to set a working directory. So those who are using Windows, once you copy your path, you just need to change it into the /. Okay, but those who are using MacBook is straightforward. And if you want to know the path, I think those who use Windows is so easy. But those who use MacBook, I just go to my desktop. I look for the folder that this folder called Nuxa China. Can you see my desktop?
Yes.
Hello.
I can.
Okay.
Yes,
So I look for this. Okay. So I look for this folder called Nuxa China. Any data that I want to import in R, I have to put it there. So you see, I have SPS data here. I have SAS data. I have STATA data. I have Excel data. I have CSV data. All the data that I want to import, I have to put it in that folder. And that folder, the path to it is called working directory. Those of us who use Mac, you can go to get info and copy. If you're a Mac user, I'm sure you know how to do that. And those who use Windows, mostly Windows, there's a bar, there's something up here that when you click, you're able to see the address directly. Just copy that address and go and paste it. Go to your R and paste. Just that when you paste it, you have to change all the backslash to forward slash, okay, before it will work. Fine. So once you set the working directory, then to import data in CSV, you don't need a package to import a CSV data. That is why if a data is in Excel, it is better to convert it to CSV before you use. And to convert it to CSV, if I should open, let's say this is an Excel data. Let me open. So this is an Excel data. If I want to save it as a CSV, I think I've done all these even in the first YouTube channel video. You just go to File, you go to Save As, just like we're saving it for the first time. Then you go to the file format, and then you choose CSV, delimited. Those who use Windows, you should be careful. There are many delimited. Even on MacBook, you see, we have delimited values. You are looking for delimited without anything. This one, those who use MacBook. And those who use Windows, you have delimited Macintosh, you have delimited with different wordings to it. All you are looking for is delimited without anything. And that is what you need. Okay, so don't forget. So that is how easy. And when you save it as a CSV, sometimes you get some message that you are going to lose certain things. No, don't worry, nothing is lost. Okay, fine. All right. So, but yeah, so it means that if you're importing a CSV data, you don't need a package. But if you're importing Excel, you need a package. So why would I need a package if I can just convert the Excel data to CSV manually, simple, and just import it without a package? Fine. But this is how easy to import. It is the name, exactly how you name the CSV data, and you bring the CSV. And that is all you need to do. And there was a data called transformed data in that's what I opened, this transform. All I need to do is to copy the name and go and paste. Okay. The moment then you get the spellings wrong, you get an error, right? So go and copy the name directly and paste. And don't forget the extension. And then if I want to import SPSS data, this is read.csv. The package is the Haven package. The Haven package is used for that. And then I just have to specify the name of the SPSS data. And now I have managed to import an SPSS data into R. Okay. Now let's imagine you wanted to save the SPS data as Excel or as CSV or as STATA or as any format. Now just imagine I have imported a STATA data. This data is the DTH, a STATA data. After importing, I am exporting it as a CSV back into my repository. So you see, the moment I run this ADP underscore Excel, right? This one, I've converted the STATA data to CSV, okay? CSV is an Excel format, just that is an Excel. So, and that data is this one. I literally just converted it to. So it means that situations where you have data in Excel, you have data in SPSS, and you want to now change the data structure or the data from SPSS or STATA to Excel, you can easily import it into R first and export it in any version you want. Okay, that is how easy it is. So that's all I wanted you to note. I mean, traditionally for SAS, there's a way to import data into CSV in SAS, but it's a long format. But in SPSS, in R, you can import it directly and you can export it in any format you want. Fine. All right. So unfortunately, I'll just give you a background information about the programming task, and then I'll attach appropriate link. So once you get access to this file, you just go to the link that I'm going to attach, and then you okay. So let me attach the link here. Where is it?
Okay.
Yeah. So here is the let me use this to bold it. Okay, so this one is the R codes for the multi-state. I'll just explain it briefly so that it will be you'll be able to work with it. Multi-state Markov model. Okay. And let me add articles for classical survival analysis. Okay. And I think this is one example. And there are many. Just if you go to Google and type how to do survival analysis in R, it's just straightforward. Okay. So I've attached those here. So it means once you click, this will be clickable. When you get the HTML file, it will be clickable for you to visit that. And fine. So now let me just explain I just want to explain the research problem. And then I just want you to know how to collect survivor data. Suppose you are doing survivor analysis and you want to collect data from the hospital. Don't just go to the hospital and tell them that I need data on this to do survival. They will not understand. They will actually give you a data, you can't work with it. So it means that you have to, most of the times, if you want to collect data from, let's say, clinicians, it's possible, maybe if possible, get a structure of the data in Excel so that they just fill it. They will just fill in those stats templates. That's the best thing, so that you get a data that is already in the analyzable format. Okay, fine. But there are instances where maybe the data you want is not in analyzable format. You should be able to transform the data and clean it and put it into the analyzable format, because you will not always get the data in the format you want. But this one is just to help you. If you want to do multi-state Markov modeling, how must the data be entered? That's what I want you to know. So this practice task, okay, is actually based on a certain disease called cardiac allograft vasculopathy. Vasculopathy. Okay, vasculopathy. To make life easier, I'll call it CAV disease. Okay, so we are saying the CAV disease is a progressive disease. So it means it's a disease that changes over time, and eventually it leads to heart failure. Okay, so by heart failure means that if your heart fails, you are likely to die. So it means eventually you could die. And it involves narrowing and blockage of the coronary artery in the transplanted heart due to chronic immune whatever. And now the whole point is that if we're to do the classical survival analysis, and I was looking at modeling the time to dying or the time to survival, okay, all I need is at the end of my study period, did an individual die or not? And if the individual died by the end of the study period, at what time did he or she die? And that's the time to death. Okay. And if by the end of the study, an individual had not died by the end of the study, then it means that the time to death for that individual will be the final time, and then it will be considered as censored data. Censored means that the individual is yet to experience the event. Even though we don't know the exact time the event will occur, we've attributed the final time as that. So we are just trying to say that the individual will die anytime after the final time. So it means to do survival analysis, your data must have censoring. At least there must be censoring. Censoring means that in real life, not all the individuals. So it means if you are doing a study, you want to do survival analysis, and all the patients you are using actually died, and you're looking at time to death. That data, since all of them had already died, none of them was censored. So it's in that case, you can't use that data for survival analysis. At least you need some of your individuals to still be alive. Okay, before you can apply these methods. These methods assume that not all the individuals actually experience the recurring event or experience that event of interest. In this case, the event of interest is death. And that is the classical or traditional survival analysis. But like I said earlier, that has limitation, because imagine situations where an individual came to the hospital healthy, And later that individual suffered from this infection, the CAV infection, and it was mild. And after some time, that individual had a severe infection. And at some point in time, that individual from severe just died. Severe means that the person is now close to heart failure. And now the person died. Or there are instances that when the individual got to the mild state, there are instances the individual could have what? Recovered back. So it means this arrow you are seeing, you can add more arrows. So I could have had an arrow that is going back towards health. It means the individual became mild and later became healthy. But there's no way an individual can move from being healthy straight to severe. And that is what we mean by the Markov property. The Markov property is just trying to say that the current state of an individual, okay, is dependent on just the recent past, irrespective of the previous state. This is to say, and before an individual would get to this state, severe state, the individual should have been mild. And I don't care about whether the individual was healthy. It means that severe status is wholly dependent on the mild state. The same thing, mild state is strictly dependent on the healthy state. And if there are instances where someone can have a mild infection and also get healthy, then there will be an arrow also going back towards healthy. And your model should be able to capture that. So here is just describing a situations where once an individual gets to the mild state, they cannot get back to healthy state. So in that case, it means someone can only move from healthy to mild, and someone can move from mild to severe. An example is HIV. There's no way you can get HIV and get back to healthy state. And maybe you got HIV, you are the mild state. The HIV has not developed to AIDS. And because of that, it looks as if you're not even sick. Then later on, maybe you are placed on ART, some therapy. And because of that, it looks like you are doing a bit better, but still you can never be healthy. You can never recover from the infection. You become healthy when you recover fully. So depending on some infections, the arrows will not go back to certain state. Okay, so that's all I want you to understand. And once you get to mild state, you either remain in the mild state or you go to severe. But we do believe that someone can be healthy and die. Someone can be at the mild state and automatically also die. Someone can be in the severe state and also die. But imagine situations where, so if you look at this paper where I use this for modeling a biological system. So this one, I was looking at survival, but considering a population of fish. Okay, so with this one, if you look at this curve, I mean this is called like a transition matrix. Here, I have 3 states. Situation where an individual, a fish is alive without the infection. 2 is a fish alive with infection. And 3 is the fish dead. And there was no way that a fish which is alive with infection, there was a way that a fish which is alive with infection could have recovered. But because of the study design, the way they designed the study, there was no way that happened. Okay, so that's why we are seeing 0 zeros at certain point. Anytime you see 0 here, it means that there's the transition from state 2 to state 1 is not possible, and so on. Fine. So this is basically what we mean by the transition graph or the transition diagram. Fine. And so it means that for every disease, the diagram would differ. Let's say, imagine if it's HIV and we have grade 1, grade 2, grade 3, grade 4 before death. It means that if you do survival analysis and you are only looking at time to death, and you ignore the various stages an individual goes through, your model is not realistic. That is why a certain famous statistician called George Box, if you go to any modeling class, that's one of the names you hear. George Box stated that all mathematical models are wrong, but some are useful. It's just to say that if all mathematical models were not wrong, even regression, then we will not have error 10. We are having error 10 because we don't think the prediction will be perfect. So it means that if you even fit a model which is too perfect that the error is almost 0, that is what we statisticians call it overfitting. We feel like it is too good to be true because we don't expect the model to be too accurate that way. So it means you can fit a model, it can be 80% accurate, it's good, at least it means it is 20% not accurate. But if you fit a model and it is 99%, 99.9%, that is a problem. That is why most of the times when we are doing hypothesis testing, we do it with 95 confidence level, because the truth is that you can never be 100% confident. And we only go for 99% confidence level when it depends on the nature of what you are studying. If you want to prioritize accuracy over anything, then in that case, we go for 99% confidence. Fine. So this is the nature of the data. So imagine a data where an individual could be healthy and later get mild infection. From mild infection, the individual can progress to severe before they die, or at any point in time, at any stage, the individual can also die. And if it was a disease where from mild you can go back to healthy, imagine if it is malaria, then from mild you can go back to healthy. And in that case, there will be an arrow towards that. Fine. So the data you are going to use is actually an inbuilt data in R. It's called the CAV data. And it is one perfect example for multi-state modeling. It helps you to know how the structure should look like. So the data we are going to use has these variables. So the first variable is just patient ID. And remember that to do multi-state modeling, your data must be what? Your data must be longitudinal. As a matter of fact, even for cross-sectional data, even for the standard survival data set, every survival data is longitudinal, because you are looking at time to what? Time to a certain event occurred. So it means patients started at time 0 and you are tracking their progress over time. So that's why almost every survival day analysis requires a longitudinal data set. You can convert the data for a multi-state back to the classical survival data set. And that's what I did in this code below. I demonstrated how, if you wanted to do the standard survival, just looking at predicting the time to death, then in that case, you need to restructure the data in a certain way. And if you want to do the multi-state, then the data needs to be restructured in a certain way. So now the data we have here is in the multi-state fashion. So if you look at this patient, so this is how the data looks like. So we have a variable called PT norm as patient ID, and their age, the age of the patient at the time of the heart transplant in years. And we also have something called a variable called years. And that years, this variable called years, it is actually the time since transplant for the recorded patient. So this is actually that survival outcome. So it's just like saying the time. So this is like the time since the transplant. Okay. So one could call this as, if I want to define it very well, I could say time to heart transplant. Okay. So because I told you for survival, the outcome should be defined like time to an event, time to event. So time to what is the event? In this case, the event is transplant. Just that we are saying that once an individual has that transplant, they can undergo any of these states. The individual could be healthy, and later on, the individual could start getting mild infection, and then later it can be severe, and at any state, they can also die. Fine. And so we have the time to transplant, and then we have age of the patient at that time. As at the time the patient got the transplant, what was their age? And we have a variable on sex, and then we have primary diagnosis that led to the heart transplant. Okay, and then we have cumulative number of acute rejection episodes for fine, and then we have, this is the multi-state. This is the state that is defining the health state, whether the individual is healthy at a particular time, whether over time the individual changed to a mild status and then maybe progress from mild to severe. This is where you track that history. And then there's a variable called first observed. This is just indicating whether the records corresponds to the first the patient first observation. This is to say it helps us to track this first observed. So for instance, if you look at patients, the first patient with ID ending at 2, so you notice that it was 1 at the beginning and 0 everywhere. So now I've extracted that patient. So for that patient, you notice that for the first observed variable, it is 1 at the beginning and 0 everywhere. This is to say the patient entered the study at this particular time. It helps us to know at what point in time the patient first entered the study. Okay, so that's what that variable is tracking. And then this state max is a variable that helps us to conclude on censoring. Okay, it's a variable that helps us to conclude on censoring. So now let's look at the definition. So for instance, this state one means healthy, 2 means mild, 3 means severe, and 4 means dead. And then now let's look at this state variable and the state max. Okay. Now, when the state is 1 and then the state max is 1, it means that individual is healthy and that individual is healthy and they've not experienced any other event. At this instant, that individual is healthy and then they are still healthy. Fine. So situations where now here the state is okay, so for here, always for this particular ID, all the states coincided with the state max. Now let's look at situations where it didn't, and let's look at how we can define. So now I want to add 2 variables, which are not in this data. So I want to add censoring status, and I also want to add survivor status, whether dead or alive. You notice that for the state, if you are in state 1, 2, or 3, you are alive. And then if we are in state 4, you are dead, right? So I want to add that as a variable to the data, such that for the censoring status, if you see 1, it indicates that the patient experienced the event before reaching an absorbing state. An absorbing state is dead state, okay? And then 0 means that the patient was censored. Censored means that they remain in that state, and or they are yet to censoring means they are yet to experience that absorbing state, that death, the death state. They are yet to experience that. And if someone is alive and they are yet to experience the death state, okay, if someone is alive and they are yet to experience the death state, okay, it means that patient is what they are yet to experience the death state and the study is not over. That patient is not censored. Censoring only occurs if at the end of the study that patient is yet to die, then that patient is censored. Fine. All right. So here, all I'm trying to say is that in order to add a censoring status, situations where the state variable and the state max variable are not the same, we are saying that that individual is censored. And situations where they are the same, that individual is not censored. And for the dead state, like I already said, once any state is not equal to 4, once we have state 1 is not 4, state 2 is not 4, state 3 is not 4. State 1 is they are still healthy, and 2 is they are mild in infection, and 3 is they're severe. Any of these, you are still alive. So here I'm just trying to say that once an individual is in any other state, which is not the maximum state 4, then that individual is what? Is alive. And then the individual is dead. 1 means dead if they've reached the maximum, and if not, then they are alive. Fine. So so it means that this is the key. 0 means alive, 1 means dead. And with this one, 0 rather means censored, 1 means 1 means that they've already experienced the event. Fine. So that's just how the data. So I've added the functions I've created here. It is not on this website. Okay. So it means for the website, you are not going to look at how they extracted their data. You don't need that one. You also do, all you need is from this part where they are talking about how to use the MSM package. So there's a package called MSM for multi-state modeling. So starting from here, then you can start using the package. Remember that they are doing the analysis assuming these possible transitions, but you could decide to assume that someone can move from mild to healthy if that existed. Okay, fine. So it means that transitions would always be dependent on what you are doing. For my study here, once an individual is dead or alive, is alive, okay, without the infection, they can either be alive with the infection, so they can either move from state 1 to 2, but they can't move from, how do you call it? They can't move from states. What was the point here? Okay, state 1 is once an individual is alive without the infection. Over time, they can have the infection or they will die. But in the data, the way the study was designed, all the fish were not in the same, let me say, environment. We studied each fish in isolation. So it means that it was such that once a fish is infected, okay, if an fish is infected, the next state is they can die or they can lose their infection. Okay, or they can lose their infection. So that was that. So it means that was the possible transitions. Either you are dead, either you are alive without the infection, and later you get the infection, and from there you die. But if you are dead, you cannot get reinfected. And then yeah, so it means that always to define the possible transitions, it is always dependent on what the disease is and what characterizes the data you are working with. And a take-home message is that possible transitions are described based on something called a transition probability matrix, and that is like what I was trying to define. I was trying to define here. Okay, in that sense, fine. So in this case, so it means that just follow this course. This course is just trying to tell the number of transitions that occur between state one to any other state, and then it's looking at how to set up the model and so on and so forth. Yeah. So that's one thing. And the beauty about the structure, the multi-state Markov modeling. So the paper that I was telling you about, this is the code that was used for that, but it's quite long, so I didn't want to. The beauty about this is that the predictors that will predict transition from, let's say, healthy state to mild state might be different from predictors that will predict transition from mild state to a severe state. So it means it can investigate much more complex directions. So it's just that's the beauty about the multi-state, that you are also able to check predictors that influence some specific transitions. So there are more you can do to it, and the mean time to remain in a particular state. And so if you get access to this particular paper, it will help you, that paper, it will help you to know the other things you can estimate from it. Yeah. So estimating probability of transitions and so on. So and giving some covariates and so on. So yeah. So basically, extracting the data, I've done everything for you. You only need to use this code and go through the modeling part. So for instance, the variables I've added, they didn't add it to it. So I created my own function to do that. The dead state and the sensor state, I've created it to do that. And here I'm able to check all the patients who were censored, okay, or who experienced censoring. And yeah. And for the censoring status, here now let's look at why the censoring status is 0. 0 means that the patient is not censored, right? So this one, anytime the state matches the state max, it means it is what? If it matches the state max, okay, then it means the data is not censored, right? But situations where here the state was 2, right? And then the next one, the next one was rather 3. It didn't match it. Then the censoring status is 1. What this means is that this patient, okay, who is in the mild state, we didn't know the exact time they remain mild at that point in time. So it meant that patient, so in that case, the possible transition they could get is what we mean by the state max here. So this is to say, if they don't agree, then we are saying that they are censored, right? And so that's basically how they were trying to use. But if I was the one entering this data, I won't define a variable called state max. I should be able to check whether that individual was censored or not. I should just create a variable. If they've not died, it means they are not censored. And then by the end of the study, if they are dead, then it means they experienced the event. If they are still alive by the time the study ended for them, then it means they are censored. Fine. So that's how I would have done that. Okay. So here, so I started. So I think I first started. So what I did here was I created a function to extract the last row of each of the patient data. But the last row means that I'm now looking at the time to just death. So the time to just death means that for each individual, I notice it's longitude now. So I'm looking at the last data for each individual. If we extract the last data for each individual, it is equivalent to the data you use for the normal classical survival analysis. Okay. But if you are now using their entire history, what all the possible transition they experience over time, then that is the second phase, which is the multi-state, Okay, fine. So I just started going through that, but time couldn't permit. So this is an example of the Kaplan-Meier curve. So here we are looking at comparing time to death between males and females. Okay, and this p-value is the log rank test result. So that tells that there was no significant. Anytime the curves between males and females, there's any intersection, then the log rank test will not be significant. But for us to see a significant difference in their survival, we don't expect the two curves to intersect at any point in time. Okay, so without wasting time, I will end here. There are a lot you could have done with it. And I think there's already a YouTube channel, a YouTube video on this survival analysis in depth and what the kind of testing you should do. I think if you look at even this video, survival analysis, the part D and the multi-state, I think I even introduced that a bit there. So you can take a look there and that's fine. So please make use of this data. So here I've done the data already. I've extracted and added variables you need to add and everything. All you need to do is to go through the multi-state codes and go through the survival code to see how we do the standard survival analysis and so on. Okay. All right. So without wasting time, I'll end here. I can take a few questions and thank you.
Hello. President, please, can I speak?
Yes, please.
Okay, this is Bernard. No, honestly, you've really done everything. You've touched on happy. I don't know what to say. I just want to know when are they going to even give you a professor from Oxford? Please.
Mercy.
Yes. It should come as soon as we will come and give it to you. Okay. So no, thank you for the to how are we going to not to bother you but to contact you or send you a mail touch from time to time. You made mention of a pizza.com. We said we should send you a link to enroll you or something. So we want to know.
Yeah, so I think at the beginning of at the beginning of my presentation, I said, okay, it's fine. Let me just put it on the chat. But if you go to Google and you type my name, Clement Chumesi, you see the first, how do you call it? This one, my Oxford University website. If you click on that, you get access to, even my number is there, but please don't call. You can text me a WhatsApp message, but that's fine. But
I've already sent a WhatsApp message.
That's fine. But my email address are there. So that's my Oxford University email address and that. So if you want me to add it to the Piazza so that you can have access to the course and everything, you can just send me the email. But for those who are part of the NUXA China guys, all I'll do is that I'll send the HTML file and everything to your president. Is it Ben? I'll send it to him, and so that you don't have to go through that stress of that. But the truth is, if you want to get access to all the course on my YouTube channel, then you really need to enroll on the Piazza. So for the Piazza, once you send me, just send me an email and indicate that you want me to add you to the Piazza platform or to enroll. I can't add you directly. You have to enroll yourself. But how to enroll is that I would. So for instance, on Piazza, if I go to where is it? Okay. Just a minute. Okay, this resources. Okay, so if I take away this one. Okay, login. Okay, so on Piazza, when I go to manage class, I will just send you. So once I put your email here, it will enroll you. So this one tells you that about 340 people are already enrolled. Okay. So once I put your email and click add, it will send you an automatic email. And that automatic email, that automatic email, there's a code that you will need, but that code in the automatic email is it's not correct. So what I do is that whenever I send you that automatic email, I send you a second email with specific details to follow. Okay, so you look at that specific details and then you come, but the link to enroll it will be in the automatic email, but you need something you call access code. And the access code is this one. This is the access code. But in the automatic email, I think the access code is wrongly defined. People were complaining that it's wrongly defined. So I send them the correct one and then specific information in another email so that you know exactly what to do. Yeah. So that's the best. I think, yeah. So that's it.
Okay. Thank you. Thank you.
No worries.
Yeah, okay. Doc, thank you. I just wanted to find out with regards to the functional data analysis, where you convert your data into curves. Yeah. Could that one be used as a form of finding whether your data has a normal distribution or otherwise?
No, not at all. So for the functional data analysis, so first of all, remember that all the statistical tests we know, ANOVA, regression, principal component, we have its functional component or its functional form. It means that all the classical statistics we do, the functional data analysis has a one-on-one mapping of each of those methods in the functional form. Okay. So it means if we want to test for normality, we have a statistical a normality test in a functional form for that. But the beauty about functional data analysis is that it is often used when you want to identify patterns in the data, especially when the data has noise. So with the functional analysis, after converting it to curves, there's some smoothing function that we can apply, such as B-splines, that can take away or denoise the curves or the data so that you'll be able to see the patterns clearly. And remember that the data must be in a longitudinal fashion before you can apply that. And it's applied to different areas of application, engineering, in medicine, and all those things. It's applied there. Think about it. Survival curves is just like a unique example of a functional curve. Just that with the survival curves, you cannot integrate or differentiate the curve. But with this functional data analysis, all the data we are working with are in the real space. It converts the data from the real space to the Hilbert space. Hilbert space means that the data are in curves that are differentiable, so that if you want to even investigate the rate of change, you can take the first differential. And the first differential, it will be the rate of change. So in that case, you'll be able to now plot or visualize the rate of change in your outcome over time. So time will be the x-axis. And then that variable that has been converted, the outcome that has been converted in functional form will be the y-axis. And you can even find the second derivative if the second derivative has a meaning. You know, I mean, especially if your data is about distance, then it means that the first derivative would literally be what? Velocity. The second derivative would be acceleration. And if it is something else, it can have different meanings. But always the first derivative is the rate of change. Sorry. I hope I've answered your question.
Yeah, that's very good.
Okay, can I take one or two more questions and let's end.
Yeah, Doc, I have a question, but just I can't find a place to raise my hand.
Oh, just talk. Just talk.
Yeah, so I wanted you to really explain the factor analysis and the PCA again for me. In summary, do you mean I cannot do any factor analysis using numerical data?
So basically, yes. So basically, factor analysis and then principal component analysis, I want to say they are similar. Similar doesn't mean the same. You know, when something is synonymous, it means they are almost the same, but not the same. It's just to say that for factor analysis and then principal component is applied to only numeric data. So it means that if you have a categorical variable that you wanted to even include in the principal component, that categorical variable has to be included as a numeric variable. By numeric means that I don't have to assign labels. If it was male was 1 and females was 2, I should maintain it just like that. But if all the variables are categorical, especially those who do a lot of questionnaire or Likert scale kind of analysis, okay, especially those who do you have some scales that there are something called latent variables. So latent variables are those variables that you cannot observe from based on. So for instance, if I ask you your age, I know there's that age. So for instance, if I want to know your academic performance, I can use your GPA or something as a metric. But if I want to know your happiness and I want to quantify your happiness score, there's just no way. But they are latent. There are some standard questionnaires to quantify all those social variables, your post-traumatic stress, your satisfaction, and all those, especially those who are into psychology. They do this kind of latent variables analysis a lot because most of the variables they work with are latent. They cannot quantify it from an observed variable. They cannot observe it, but they can use some indicators or some construct to help quantify those latent variables. And so basically, it means that in order to do factor analysis, first of all, the variables must be categorical. That's for factor analysis. But for how do you call it? Principal component analysis, the variables must be numeric. But one thing I have to advise is that factor analysis has two types. So we have the confirmatory factor analysis and we have the exploratory factor analysis. Okay. So for the confirmatory factor analysis, structural equation modeling combines the confirmatory factor analysis and path analysis together. So the path analysis are just set of regressions. As you can see, with the structural equation model, there are set of regressions you are interested in, and you want to investigate them at the same time. And that structure, okay, you want to confirm that structure. That is what we mean by confirmatory factor analysis. You want to confirm that structure you've hypothesized. But I was saying that if you don't even know the kind of structure, then you can couple hierarchical stepwise regression with moderation mediation analysis in order to get a potential idea or a fair idea about the kind of structure your SEM should look like. And then you can now confirm with structural equation model if that is the case. Fine. So in summary, for factor analysis, especially if you are interested in using it for dimension reduction or reducing the dimension of the data, especially if you have a scale to quantify a latent variable, and you believe that not all the variables are important, and you want to know which subsets are more important and the ones you should take out, it's going to employ some principle of principal component. But if the data is categorical, that principle is based on factor analysis. And if they are all numeric, then it's based on principal component. But remember, never include the dependent variable as part of PCA or factor analysis, especially if you're reducing the dimension of the data. Okay, all right. And those who do like proteomics and genomics, they do PCA a lot.
Thank you, Doc. And so in that case, how is the factor analysis different from logistic regression?
Oh, logistic, you see, like I said, for factor analysis, we are just reducing the dimension of the data, just like principal component is doing. But logistic regression is when you are looking at factors predicting some categorical outcome. So it means factor analysis is not a regression. PCA is not a regression. It's not a regression. Logistic regression is a regression model where the dependent variable is categorical. If the dependent variable is discrete, then it's Poisson class of models. An example of the Poisson class of models is Poisson regression, quasi-Poisson, and negative binomial regression. And situations where the dependent variable is continuous, then we have OLS class of regression, generalized least squares, and or even ANCOVA. Yeah, unfortunately, I didn't talk about ANCOVA. You see, the difference between ANOVA and ANCOVA, you see, ANOVA is like you are comparing some continuous outcome between three or more groups, right? But imagine where you have a situation where you have a data you collected at baseline at time 0, and then you collected that data at a future time point. and then you wanted to look at comparing the difference in looking at how the feature or the post-baseline data differs between your treatment groups or some categorical variables, and adjust for the baseline variable. In that case, that is what we mean by ANCOVA. And remember, it's not just baseline. Think about it as any instance where you have a certain variable that is not a predictor, but it co-varies with the outcome. This is to say, once the outcome changes automatically, that also changes. Then you can add that variable that co-varies with the dependent variable in any regression model. And the moment you do that, example is the baseline scores. If you add a baseline score to any regression that you've been doing, that regression model is called ANCOVA model. So ANCOVA is just like adding any variable that co-varies with the outcome. It doesn't necessarily have to be baseline scores. It could be instances where it could be, let's say, you have immune response, and then you have a certain variable that automatically, once it increases, immune response will also increase. So it means that it's highly correlated with the outcome. You can add, because remember, we said for regression, we expect the predictors to have high correlation with the outcome. So it means that even if other predictors are not highly correlated with the outcome, but you are able to identify a certain variable that co-varies. By co-varying means they are highly correlated with the outcome. Then what that means is that it's going to help improve the model because of the high correlation just that variable has on the outcome. So that's basically, in that case, you are using that in a way to improve the strength of associations of the other predictors on the outcome. So that's what we mean by ANCOVA. And with ANCOVA, you can also include interaction effect in the model. Yeah, so basically that, but you can do ANCOVA without interaction. So all the regression model you've been doing, the moment you add the baseline scores and you are predicting some future time scores of some outcome, that is an ANCOVA. You can include interaction effect, and it's still an ANCOVA. Have I answered you? Usually I answered your question more than you need. So that
You've done well.
okay. Okay, so I think we should probably end here because of time.
Yes. So, Doc, we thank you very
Well,
much. I think the president can speak now.
Thank you
President.
very much, Doc, for the question. Unfortunately, Bernard, we cannot allow you to continue because we are going to end it here. We
Okay, thank you.
3.5 hours into the training, and Doc is tired. We need to let him go. So perhaps you have his details, and you can send him your request and all other questions personally via mail or via chat. So
Okay.
all right.
Please,
On this
I would
note,
need
I would say a very big thank you to you, Dr. Clement Chumesi, for your time with us and for an insightful presentation. We have learned a lot within this short 3.5 hours. I think you've taught us from grade 1 statistics to very advanced
We are
statistics.
now.
And we are very, very, very grateful for that. So Doc, on behalf of the HICF leaders, I would say a very big thank you. On behalf of NEC Nukes, I would say a very, very big thank you. And there's a proverb in our language that if the housefly has nothing at all, at least it has its hands to rub each other. So I would call on the Vice President of NEC to present something little that we have put together to appreciate your time and the effort that you have put into this. Vice President, Your Excellency, you have the floor.
Hello, sir. Please, is my president here? Madam President, are you here? Madam President? Madam President is here, but
Honorable Ben, I'm here.
All right. Please, Madam President, do us the honor.
Thank you very much, Honorable, for giving me the platform. And Dr. Clement, I want to say a very big thank you before reading our citation. God bless you for taking time, 3-4 hours out of your time to break this whole hour software down to our level. God bless you. I want to take the opportunity to read our citation. The entire membership of the National Union of Ghana Students, NUGS China, would like to express our sincere appreciation to Dr. Clement Chumesi in recognition of your outstanding contribution as a distinguished speaker on our statistical software on December 7th, 2024. Your insightful knowledge, expertise, and engaging presentation have not only broadened our understanding of statistical tools, but have also inspired us to explore the power of R in research, data analysis, and academic pursuits. Your dedication to empowering students with practical skills and your commitment to academic excellence reflects your exemplary leadership and passion for education. We deeply appreciate your willingness to share your time, experience and wisdom with our union. Your impact on this event will resonate beyond today, fostering a stronger academic foundation for Ghanaian students across China. With profound gratitude, we honor you and your invaluable contribution to the success of this program. God bless you, and a very good evening to you. Thank you.
Thank you very much. Thank you very much. So please, I will entreat you to encourage others to subscribe to the YouTube channel and learn at their own pace. I don't get anything from it at this stage, but I think for me, I'm just more interested in always making that little difference. And the lives I touch, to me, is more rewarding than even money or than anything. And I encourage most of you to also do the same when you develop if you have any expertise that you think others could benefit from it. I think in that way, it might look like you're not getting much from it, but the truth is that people are watching from afar. So I also thank you for the opportunity. It's been like over 5 years or so that I've been doing this every year, and I'm always happy to help. Yeah. So thank you very much, and I'll be happy to get the citation sent to me privately.
Sure. It would be sent to your email after the training, and we will share your social media platforms, that which would need to be subscribed to our members to do the needful. Yeah.
Okay. All right. Thank you. And I'll be happy to get the recording so I can put it on the YouTube channel. And I'll try and split it and take away things that are not important, and so that it will just be focused on the statistical bit and people can just watch it in a better way. Yeah. So thank you very much.
You're welcome, sir.
Thank you. Mr. Johnson.
All right. Yeah. Bye-bye.
All right. So thank you very much, Doctor, once again. We know that no amount of whatever we have can actually replace what you have done for us, but we are grateful for supporting our research with your insightful presentation. So on this note, I would bring the meeting to an end. And like we said, this scale up is a process. We'll be having some other courses coming up next week. So next Saturday, we'll be looking at how students can write articles in LaTeX. So there are several other courses coming, data analysis with Python, data analysis with other softwares coming up. So we hope that the numbers that turn out today would do so in the subsequent training as well. And Doc, in case, going forward, we find some topic that we believe you can give a very extensive talk on. I hope you wouldn't mind if we reach out to you once again.
Oh, no problem. I mean, so for instance, all the publications I showed you guys were all written in LaTeX.
Okay.
So I use LaTeX for everything I do. Okay, no worries.
I understand, but we have a speaker for LaTeX, so I'm just saying in the near future if we need
to be a speaker for LaTeX.
exactly.
But if it's about maybe empowerment, if it's about future career, like how to that kind of thing, anything, anything academic, that's fine by me.
Most definitely. Thank you so much, Udo, once again for your time. And thank you all members of NUGS and HICF that made it this evening. We hope that we can hear from you and see you sometime next week. So on this note, we adjourn the meeting to next week. Have a
Right.
wonderful weekend and an evening as well. Thank you all for coming.
Okay,
Thank you, Dr.
thank you.
Bye.